Lesson 8, Optimizer, Table and Index Access Paths. And we certainly have talked a little bit about these already. We're going to formalize that discussion because we've talked about some queries use full table scans for certain tables, some use index scans. And we looked at the way you write your SQL and how you use the predicates to influence whether or not we can use an index. Now we're just going to formalize the information about the execution plan. After completing this lesson, you should be able to describe the SQL operations for tables and indexes, list the possible access paths for both tables and indexes, and then at the end we have a list of common observations and questions that people have had. So first up, we're going to look at the row source operations. So row source operations are returned by a step in execution plan. It's a number of rows to be fed to the next step higher up the execution tree, essentially. The row sources can be classified as unary operators, which are the access paths that we're going to discuss in this lesson. They can also be described as binary operators, which are the join methods that we're going to discuss in the next lesson, in lesson 9. And there are n-ary operators, okay, that use more than 2 inputs. We're going to discuss those in lesson 10. Okay, there are set operators and things like filters that potentially take more than 2 inputs. An access path is a way in which a query retrieves rows from a row source. So now that we've discussed the row source operations, we're going to look at the main structures for storing data and the main access paths we have. So our main structure for storing data are the tables. And there are exactly 3 access paths that we discuss for them. One is a full table scan, one is a row ID scan, and the last one is a sample table scan. We use indexes if we want to access a small number of rows in our tables, and for the indexes we have more access paths. We have an index scan unique, a unique scan on an index on a unique index. We have an index scan range, full, fast full, skip, as a skip scan on the index, index joins that we've seen already, bitmap indexes, and we can combine bitmap indexes as our fundamental join methods. Actually, around the bitmaps, there's a little more details than that, but we'll look at some of the details when we get there. So first up, we're going to have a look at the table access paths. First up in the table access paths is the full table scan. When we do a full table scan, we don't read one block at a time. We do them chunks at a time if using the DB file multi-block read count. If it's been explicitly set to 4 on the database, or if we auto-tuned it to 4, we go through the data 4 blocks at a time. Okay, we'll grab a chunk of the first 4 blocks, grab the next 4, and we have to keep looking at data until we get to a little marker called the high water mark. The high water mark marks the last set of last block. Anything below the high water mark or to the left of the high water mark has had data for the table in it. We won't guarantee it currently has data, but at one time it has data. We got to look at every block and every row logically to the left, or what we call lovingly below the high water mark. Any blocks to the right belong to this particular object table we're looking at, but they've never had data inserted in them. We don't need to consider them as part of the full table scan. Okay, so it reads all the formatted blocks below the row. It needs to look at every row and apply filters, okay, if they're available. Okay, And it applies them by just looking at the row and looking at the predicates and seeing if it can apply them. If we are returning large percentage of the data, it can be the best access path. Even though in the past it's been much maligned, it's actually a good access path if we want the majority of the data. It's faster than actually using an index. And this is just what it shows up in the execution plan. We've seen it already. Table access. It's doing a full, as noted on the options in SQL Developer, and it tells us the table over here. And the predicates is going to apply as it reads each block in the employee name equals King. It was from one of our previous examples of having a look at Mr. King. Okay, some common questions. Are all full table scans bad? No, not necessarily. As I said, if you want the majority of the data, it's a good choice. At what percentage of data does the optimizer consider a full table scan is the most efficient method to retrieve data? And they have some examples, 20, 30, 50, so on. That's actually a really difficult question to answer because it takes a number of things into account to decide this. It's just generally best that if we have a few number of rows relatively, it's more likely to use an index than if we're looking for 50% or 75% of the data. Okay. When will it use a full table scan? Well, if there's no suitable indexes. Well, you didn't give me any indexes I could use. Full table scan will always work. If the predicates we have low selectivity, 1,000,000 rows, 2 answers, A or B, they're both equally likely, I'm doing a full table scan. Even if I only want half of them, I'll do a full day. It's not selective enough. It's got to return a few percent of the rows, not half of the rows, to be useful. If it's a very small table, it may be more efficient to read it as a full table scan than try to do an index. A very small table may be readable in one multi-read count. If it's less than 4 blocks and it's set to 4, we can read it in one I/O. To use an index really implies using 2 I/Os. So it can make a decision to do a full table scan on a small table, even if an index is available. And in the statistics for the database overall, we document 2 table scans as full table scan. One is a short full table scan. We did it on a small table, and even on an OLTP system, we don't consider it a problem. A long full table scan is indication we had to read many chunks into memory. And that's the traditional full table scan. For a pure OLTP, we would expect it to have an index. In theory, it shouldn't do a long full table scan. In reality, the world isn't perfect. It does some full table scans. Long full table, but we should try to minimize them. Another time, if we can do a high degree of parallelism, we can parallelize it and we can overcome the fact that we have to retrieve more data. So if we can do a really high degree of parallelism, it can be faster to do a full table scan than use an index that we always have to do serially, unless it's a partition table. Full table scan hint is used. We hint full, and then the table name or the alias, that says for this table I wanted to do a full table scan. And that will do it, unless, and it can always do a full table scan, so it should always avoid the hint. Okay. Next up is a row scan. Okay. It can be seen in one of 2 methods. The first one they put in, table access row ID, and then just that. Usually it gets seen, use row ID after an index scan. That's the most common occurrence. We probe an index for a value. If it gets a row, 1 or more row IDs returned, then probe the table using those row IDs we found. Developers can also use this style, and it's handy in some applications. if I'm going to retrieve some data and then do a bunch of other things before I do something with it within the same transaction or the same session, what I can do is save the row ID in a variable within my session. And there's no faster way to look it up again. I went and used an index to get it, then I can save the row ID and I can go back and get it again just by the row ID. Using just the row ID is faster than using the index to find the row ID and then using the row ID to retrieve the data. Don't save the row IDs in a table. If you do that, somebody exports, imports the table or does an alter table move, the row IDs all change, and Oracle doesn't maintain your table. Your application code needs to do that. That's a lot of maintenance effort. We suggest highly you don't do that. At least that's my personal suggestion. But we can see both of them. But saving it within a session actually makes a lot of sense for some applications. The last one usually gets seen because either the automatic gather statistics job is running on the database, which usually runs at night, or somebody is using DBMS stats package to gather statistics on one or more tables or indexes. Okay, and that's the usual case. In reality, developers can actually use it. And I used to say, it's been around for a while, last year or two, I've been saying people, I haven't seen anybody use it in their application. And lo and behold, I found a person on the last time I taught this class that actually wanted to do that. And they were really interested and were exploring it after I showed them. I've discussed it in this lesson and showed them where the information is. There's additional information in the SQL tuning guide in the database and in the documentation for doing queries against the database. So we have a little quiz on the full table scan. So let's read through it and give you a moment to contemplate it. A full table scan sequentially reads all rows from a table and filters out those that do not meet the selected criteria. True or false? And the answer is true. We just go through it sequentially. We happen to do it in multi-read chunks. Whether we tune it or somebody has explicitly said it doesn't really matter to us. But we do it in chunks because we're going to do the whole thing. Makes more sense doing bigger chunks on them than smaller if we have to do a full table scan. Next up is looking at the index access paths. So we'll do a little overview and then we'll get into the details of the individual access paths. So indexes, they're a technique of creating additional structures that really in reality, a lot of cases store a subset of the data from the table to allow us to faster access to the data table. The most common ones are called balanced tree indexes. They're the default and most common. They have a number of subclassifications. They can be normal, regular, run-of-the-mill balanced trees. They can also be function-based indexes. We introduced that a while ago, and we saw an example of using that when we had the percentage ing we were looking for by using a reverse function in a function-based index. We also have what I call indexes taken to extremes, okay, called index organized tables. We also have the bitmap indexes, and we saw a little bit of working with bitmap indexes in lesson 4. We're going to look at a little more details in this one. And we also have clustered indexes that are used for clustered tables of a particular type. The indexes can have a number of attributes. They can have column compression, but to do column compression, I have to have more than one column in the index. I can't compress an index if it only has one column. We also have problems with what we call hot nodes. If we're using a monotonically increasing key to insert data, perhaps generated by a sequence generator, then all the input occurs on the right side of the tree, and it becomes a hot node because of the inserts. And also, we generally want to know it. If this is the checks for a system, for our financial system, we print checks to give to our suppliers. People want to know, was the check number printed? Was it shipped by mail to the particular supplier, delivered to them? And was it cached? So we query on the latest data. The older data start looking historical. Once in a while, we run a big report on it. But for the OLTP, it really becomes right side. A reverse key is one of a number of ways of fixing that today. The downside of reverse key index is it breaks range retrievals. So sometimes using these features is you pick the one that is the lesser of two evils, the one that gives you the minimum impact. Sometimes losing range retrievals is a bigger issue than the hot node issue. Sometimes it's the other way around. And there are other solutions for the hot node problem. Okay, indexes are normally created ascending. In fact, at one time that was the only way you create it. They can now be created ascending or descending. Even though they're created in one direction at any one time, it's the order we sort the data. They can be traversed either forward or backwards when we do a range retrieval. So it actually works out well. Now these are what we've talked about now are the standard indexes that Oracle comes with out of the box. If you don't like any of our standard indexing type, Oracle is fully extensible. You can create your own indexes called domain indexes. Okay, and most of the customers I've talked to when I teach classes aren't using domain, because it's one of the questions I ask commonly when I teach in class or on the web. And very few people have created their own domain indexes. Quite a few have used them by using some of the Oracle products that take advantage. If you're using Oracle Spatial to store GIS data in a very flexible format in the Oracle database, then you're using domain indexes. Today, the vector data uses R-tree indexes, and those are domain indexes. But who created those? They were specially designed customizable indexes that were created just for spatial by the spatial engineers. So they rolled their own type in that case. But you see them, you have them if you're using spatial or if you're using the Oracle Intermedia option also. Next up is a little picture of our normal indexes. They are tree structures. In reality, they start out, if you put an empty index on an empty table, it starts out as one node that acts as the root and the leaf. As you add more data, we split that node eventually, and we sort of build it from the bottom up to the top as you're doing it. Okay, so they become tree structures. At the top, we have the root. Information in the root node, which actually fills every node, fills exactly one block. If you've got an OLTP system, the most likely block size is 8K for it. It's the one everybody finds works well, even though we support other block sizes. And each of the nodes in the tree is exactly one block in size. And their information in this one, what tells us which of the branch nodes to go to. Values less than a certain value will go down here based on the key or keys. Values less than another one will go down here, and values less than something will be in here. So we know the max because we have a max value up here. One thing we don't store is the very right first entry, which is the min value. It would actually simplify to a certain extent the skip scan processing if we did, but they didn't. And the index can have a number of intermediate branch levels. We only showed one, but it can have a number of them. At the bottom, we have the leaf nodes. So I can pick a key value, decide which of the 3 branches to go. Maybe I go down here. Maybe this is an employee ID. I'm looking for an employee less than 2,000. So less than 10,000 is down here, less than 5,000, less than 2,000 is down here. I'm looking for 2,000, go down here. Okay. No, it's less than 2,000, 2,000 is in here. Okay. When I go here, it will tell me maybe less than 1,500 is down, 2,500 is down here, less than 3,000, less than 4,000. We can go down and discover which one to go to. Once we get to the bottom, it has a number of entries. Each of the entries look like this. Okay, the entry has an index header that stores some overall information for this entry. And then it has a counter and a column value in pairs. How many characters are in this key and a counter for it. How many characters? And this is an example of having 2 columns in an index. They're stored as a pair of column information, and it's stored as a counter and the key value, a counter and the key value. And then finally, when we have all the keys, if we only have 1 key, we only have 1 counter and 1 value for the key. At the end, we have the row ID. Okay, and it points to a particular row in the table. When we create the entries, each of the entries within a node is sorted. Employee ID 1, if we have 1 to 1,000, will be in the first 1, 2, 3, 4, 5, until we fill up it with all these entries, as much as we can hold at a particular time. Then we'll continue, and the next ones will be here, and they're double linked lists together, which is a major advantage during range scans. We can dive the index and walk in either direction to find a range of values for a particular key or sets of keys. So it gives us a major advantage. Now we're going to have a look at the index scans. So the type of scans we support are unique, range descending, range or range descending because ascending is the default, skip scan, full, index scan, fast full scan, and index joins. First on up, we're just using this tree structure to advantage. In each one of these, if this turns out to be a unique index, we'll just back up. There is actually 1 entry for every key, combination of keys. If it's a non-unique index, we can have duplicate set of keys with multiple row IDs pointing to different rows. We could have 1 key that's duplicated and it could point to 4 rows. If it's unique, it will point, 1 key will point to exactly 1 row, or we won't have an entry. Because we don't document rows that have a null for a particular column. We knew that was a problem when we count things. Okay, so we can do a unique scan. The optimizer considers a unique scan if an SQL statement contains a unique or a primary key constraint, or a unique index or a unique constraint, because both of these we support with unique indexes. And it will return 0 or 1 row. Okay. When all the columns of a unique tree are specified with equality predicates, if it's multiple columns in the index. If there's 1, we have to specify it with a unique value. If it's multi-column, we have to specify a unique value for each one generally. And it will just dive the index and find if it's a unique column and a unique value, it will find the 1 row ID and return the data. We document it in the execution plan as index unique scan on a particular index. Usually we see it followed by a row ID scan. Some cases the index can provide everything the database needs, and then we might not see the table scanned by the row ID. So this we did a select against the employee number with a particular value. It's the primary key. It will do a unique scan on a unique index. Okay, range scans as another type of scan. The optimizer considers a range scan when the optimizer finds one or more leading columns of an index specified in a condition and any combination of the previous conditions or these. When it can use a unique or a non-unique index. A lookup of multiple values on a unique index is treated as a range scan. We want to look for employees between 1,000 and 1,005. If the smallest enough range, we can do a range scan on the unique index. Even if we're looking up a single value on a non-unique index, we treat it as a range scan, or if we're looking up multiple values. Okay. It may use a range scan or a full table scan if it can avoid a sort when the column that is indexed is being used in an order by, a group by, or both. Okay. And we can guarantee we don't need to worry about nulls. So there's a not null condition on one of the columns, or we specify the not null condition as a prerequisite. We're not interested in the null values, so it tells us we don't mind missing them. But if the nulls aren't documented, and we don't have a not null constraint, or we don't say in the query we want to ignore nulls, then we can't use the index. So you have to be a little careful. And they show up as an index scan. Whoops. In the execution plan, they show up as an index scan of a particular range scan of a particular index. So we can do range scans either ascending, which is a normal, assuming this is ascending index, it dives it and goes one way. It can also dive the other end and go backwards. So it can do a descending range scan, and that's usually because the order by specification, one way to get them is we describe we wanted ordered by department, but we wanted it backwards. Because they're double linked lists, we can divide one end and walk backwards to get the range. Unfortunately, the little line underneath to indicate the range that we're looking at didn't quite line up with where they started the scan. Sorry about that. So if it's a non-descendant, it will just say range scan when we're accessing an index. If it's descendant, it will add the descending keyword. Descending index scans, okay. So we're dropping our department number index, create the index IDX on the employees and create it descending. And then when we scan it for values less than, we're going to do a range scan on a descending index. Whether the scan is ascending or descending depends on which order the index itself is in. So it changes. So it gets a little confusing, to be honest with you. Index scans can be done on a function-based index. The optimizer considers a scan when frequently executed SQL statements include transforms columns or columns and expressions in a where or order by clause, and we created the appropriate function-based index. So in this case, we're going to create one on employee's name in the employee table. We didn't have triggers or before insert trigger to filter the data, or didn't have other software in the application to control how the data was entered. So we don't know if somebody entered all uppercase, all lowercase, or mixed case. Quite often they can do it different way depending on how they feel if the application didn't have the control built into it. So what we may need to do is, we don't know what it is, we want to do an upper on e-name so we can compare it to the upper name version so we know what it looks like all the time. If we use a regular index on the employee name, it won't work. We create a function-based index that can use this index to do a range scan. So we'll tell you the index name, so they just call it FBI for function-based index. And we're doing a range scan on this to answer the user upper name like %. And that's what we're filtering the data with this particular index, our access filter. Next up, it can do index full scans. The optimizer considers an index full scan when all the columns in an order by clause must be in the index. If they're all in the index, they have to be for it to configure. The query requires a sort, merge, join. A group by clause is presented in the query, and the column in the group by clause is presented in the index. So they're doing just a little example with an order by clause. Select star from employees ordered by an employee number. Okay. And if we have an index that has the employee's number ordered, if we do a full scan on it, we can avoid an index. We can also use a range scan to avoid an index. Unfortunately, the fast full scan cannot. And with the full scan, what we do is just dive one into the index and then logically follow the linked list to get all the data sorted. They're sorted in each node, and then the linked list maintains the ordering across the whole set of values, so we can follow it to get the data ordered, and that allows us to get the data ordered without a sort. The bigger the table is, the more advantage this is basically to the optimizer.